Right, let's jump straight into this explainer, because honestly, we've got a major issue to address today. Every single year, literally thousands of Cambridge Biology 9700 students bleed crucial marks on topic 3.1, the lock and key and induced fit hypotheses. And you know what the most tragic part is? They aren't losing these marks because they don't understand the biology. No, they are losing them because of one tiny, totally avoidable, fatal error in how they present their knowledge to the examiner.
Just picture this for a second. You're sitting in the exam hall, you've done all the complex enzyme reaction rate math perfectly, and you arrive at the exact correct numerical value of 4.5. But then you get your paper back and you see absolutely 0 marks awarded. Why? Well, because you forgot the units. Or even worse, you completely ignored the highly specific, unfamiliar context given in the stimulus prompt and just vomited up a generic textbook answer. Today, we are going to fix that completely. We need to entirely rethink how we approach the theoretical architecture of enzymes, and it starts right here.
Section 1. Core Concepts and Definitions.
Okay, let's ground ourselves in the basics. The lock and key hypothesis requires a perfectly precise, rigid fit from the very beginning. The absolute key phrase here, the one examiners are desperately scanning your paper for, is complementary. Not similar in shape, not matching, but exactly complementary. It assumes the active site is a completely static, unyielding structure. It's exactly like a stiff metal lock waiting for one very specific metal key.
Now, the contrast here is where things get really interesting. The induced fit hypothesis is entirely dynamic. It proposes that the enzyme physically adapts its shape to create that perfect fit. Pay close attention to the phrase conformational change. If you just write it changes shape, well, actually, scratch that. You might scrape a mark for changes shape, but if you write undergoes a conformational change, you are instantly proving absolute mastery of the principles to the examiner. That's the top-tier terminology.
And this is exactly the causal relationship examiners want to see you write about. Static structural models versus dynamic ones. Lock and key is rigid and static, whereas induced fit is dynamic and adaptive. Deeply understanding this fundamental dichotomy is literally your foundation for scoring high marks when you're asked to evaluate or compare these models in a high-stakes question, which perfectly sets us up for our next crucial step.
Section 2. The Method Mark Strategy.
Okay, listen to this direct quote straight from the Principal Examiner report. Even if your final answer is wrong, method marks can save you. Think about that. In just a moment, I'm going to share a specific examiner clue that completely shifts how you structure your answer. But first, you need the underlying framework that makes this clue incredibly obvious, especially when you're sweating under exam time pressure.
So, the non-negotiable rule here is to follow this standardized sequence every single time you process a 3.1 question. Step 1, identify the key elements in the unfamiliar context. Step 2, apply your core biological principles. Step 3, execute your analysis with exceptionally clear working. Step 4, verify your results. And Step 5, present it using that top-tier terminology we just talked about. By putting all your clear working on the page, you're literally capturing those vital method marks as a safety net, even if you make some silly calculation error right at the very end. But now, we've got to escalate to the most rigorous part of the whole exam.
Section 3. Perfecting Comparative Analysis.
This is the real battleground. This is where we handle and evaluate information, and it absolutely separates the top-tier candidates from everyone else. When an examiner asks you to compare these two hypotheses, you absolutely must check off every single one of these analytical requirements. You cannot just list a bunch of facts about lock and key and then separately list facts about induced fit. No way. You have to actively identify similarities and differences. You've got to use comparative connectives like whereas or however. You must support each point with solid evidence from the stimulus, and finally draw a concrete conclusion. Let's make this practical. Pause for a second and think about this mock prompt. Compare the lock and key and induced fit hypotheses in unfamiliar context X. Seriously, how would you structure your answer to this exact high-stakes question right now? What specific words are you writing down?
Let's break down the difference between an average, mediocre answer and a top band answer. A typical flawed answer just states, lock and key is rigid, induced fit changes shape. I mean, yes, it's biologically true, but it's going to score terribly. Compare that to a top band answer. Whereas lock and key features a static active site, induced fit undergoes a conformational change, yet both rely on complementary shapes to catalyze reactions in context X. Boom!
Look at that. It uses a comparative connective, whereas. It highlights a clear difference, static versus conformational change. It points out a similarity, complementary shapes, and it ties the whole shebang directly back to context X. That is exactly how you guarantee full marks, assuming, of course, you avoid the biggest traps set by examiners.
Which brings us to Section 4, Top 3 Examiner Warnings.
The absolute crux of the matter comes down to these 3 incredibly common mistakes. The number 1 mistake? Forgetting units on your calculations. It's just an immediate, totally unnecessary mark dropped. Number 2, unchecked terminology. If you're writing changes shape instead of conformational change, you are failing to demonstrate mastery, period. And number 3, which honestly breaks my heart every time, ignoring the context. If the prompt introduces a highly specific, novel enzyme found in a deep-sea hydrothermal vent, and you just regurgitate a generic textbook answer without ever mentioning that specific environment, your score will be destroyed. You must integrate that stimulus material.
So how do we systematically bypass those 3 fatal mistakes? Easy. Always run your thinking through this simple 3-step problem-solving loop. Step 1. Deconstruct the question and extract the actual data from the stimulus. Step 2. Solve systematically. Break the problem into logical chunks and physically show you're working on the page. Step 3. Evaluate and check for reasonableness. Just take a breath and ask yourself, does this answer actually make sense in the context of the biology I know?
Before we wrap this explainer up, I want to permanently cement the number 3 in your mind. Remember these 3 absolutely vital takeaways today. First, define the structural differences perfectly, using terms like conformational change. Second, always show your systematic working to scoop up those crucial method marks. And third, connect every single answer to the specific unfamiliar context given in the prompt. If you do those 3 things, you are going to excel.
So you now know the biology, you've got the framework down, and you know exactly how to dodge the biggest examiner traps. But here is the ultimate curveball for you. What if the examiner command word in the prompt isn't compare? What if it's evaluate, or explain, or describe? Because if you misread those hidden command words, none of the beautiful framework we just discussed even matters. You could write a biologically brilliant answer and still score a flat 0. So, to make sure that never happens, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE and join me in our next explainer where we are going to decode the exact command words that dictate your final mark band. You definitely do not want to miss it.